All right, hey Precalc 12B, I'm going to be doing something called Infinite Geometric Series, and I am back in my classroom, so things are a little bit weird, a little bit different, not set up the same way. Using the laptop, I think it's working okay. So we'll try it out, and hopefully this is our last formal kind of like textbook lesson. Probably going to give you some review type questions that you can go over next week, but this is the last topic that we are going to be covering. So 1, 2, 3, here we go. Now, what do I mean by an infinite series, first of all? Well, so far we've talked about something that I've mentioned as being partial sums. So partial sums are the idea that we can add together the first n terms in a sequence. So if you have, for instance, the first 20 terms, it's just t1, t2, t3, all the way through t20. And s20 would just be if you took all of those terms in the sequence and added them together. So a partial sum, you can understand how that can be done in every single case. It makes a whole lot of sense. It's a finite list of numbers, and you can always add together a list of numbers and not have any problems doing that. Adding's very forgiving that way. It doesn't really bump into any problems. Dividing a list of numbers might be problematic if you ever are dividing by 0, for instance, or something like that. So it's not always okay, but adding, it is. Finite list of numbers, you can always add two numbers together or keep a running total. There's never going to be anything going weird with it, so cool. So partial sums, great. Now, a series, versus infinite. I don't know where the rest of that went. Versus an infinite series, which is basically, well, sometimes we call it S infinity. I gotta take these markers out. I don't actually want them there, and I want to use my finger. It's a little quieter. Mike picks up the markers really nasty, apparently, my wife told me. So, all right, S infinity. That is the kind of shorthand way to say that we're interested in this sum for an infinite number of terms. Now, right off the top, if you think about this seems really weird, because if I just tell you to add 1 to 2 to 3 to 4 to 5, and you have to go to infinity, what's the answer? And so it just gets bigger and bigger and bigger. So the answer is that it doesn't really have a real number answer. You can always just add one more value, and it just gets even bigger than whatever it was before. And you can't really describe how big that is because it doesn't ever stop getting bigger. So you might just say it's infinity, which is, I guess, okay, but it's not a real satisfying type of answer. So what's the whole point in having a section then on infinite series if all you can do with them is basically say, hey, they just get real big? It's a good question. So this is another way to write an infinite series. It's basically saying that you're taking the limit of the partial sum. So you are adding together a partial sum of numbers, but you're allowing that number to become as close to infinitely large as you can define it. So it approaches infinity. It keeps going and going and going, which might be a little bit nicer to say because limits kind of fit with this idea of infinity a little nicer than just saying S sub infinity. Like, well, infinity is not really part of a real number system, so what's that mean? But, this is the shorthand and a lot of people use it. All right, so like I was just saying, if I got you to add 1 to 2 to 3 to 4 and you kept going, that would become a problem. If you add 1 to the even, not the even, doubles, 1 to 2 to 4 to 8 to 16, etc., you would also bump into a bit of a problem. So that's, again, not really satisfying and would lead to a very, very short lesson. Both of these types of series, not this one here, the first one that I have written down, not both of them, that is an arithmetic series. So each term is different by some common difference. So the common difference here is 1. So 2 is 1 bigger than 1, 3 is 1 bigger than 2, 4 is 1 bigger than 3, and it would keep getting larger and larger. It doesn't matter how small that common difference is, the numbers grow. And even if the common difference was negative and they were getting smaller for a little while, they would become negative and they would start to grow in the negative direction. And so we would basically end up with either going out towards positive infinity or going out towards negative infinity as the limit as n approaches infinity of Sn for any arithmetic sequence. That's really boring. There's basically two options. You either get really big and you're positive, or you're really big and you're negative. And that's why we did not cover infinite arithmetic series, because that's the whole story, folks. So it's either infinitely large and positive or infinitely large and negative. All right, this one's geometric. Now, this is a problematic geometric sequence. This one goes 1, 2, 4, 8. So this almost becomes more of a problem faster. Not that that's actually true in terms of getting to infinity faster. What's that mean? But you can see that it's just going to spin wildly out of control, and we're just going to become larger and larger and larger with each new term that we add on to that. So that's kind of what happens when we're thinking about this S infinity sort of idea. So are there any circumstances, I just realized that's kind of off there, for which it wouldn't just be this nonsense infinitely large number? So what I want you to do is take a pause, pause me if you want, and think about whether you can, now I'll help whittle it down a little bit. We're going to look at geometric. Specifically for a geometric series, what could you do that would cause that geometric series to not just get super duper duper large? All right, I'm going to keep going, but hopefully you've given that a little bit of thought. So first of all, what we have just talked about a few times over is a I should have done a better job. I didn't realize, again, it's just my setup, but I didn't realize how, that doesn't even seem right. I thought I had fixed that. Anyway, it is what it is. So I'll just move things as we get to the next part, but sorry about that for parts of the screen being off of the little pad that you're watching. So it is a divergent series is one in which there is no finite sum. So that's where we say, oh, it just goes towards positive infinity or negative infinity. A convergent series has a sum that is a finite value. Okay, so we still haven't bumped into one of these things yet, but apparently it has a name, and it has a section in the textbook, so one would think that they must exist. So we already answered this. Never. Maybe you've answered this when you pause things. Maybe you came up with something that would allow this to happen. I'm going to leave that blank still, and I hope my next page is squares. It is. Okay. I'm going to answer that a little bit better in a second. So I'm going to introduce you to my square, and this particular square is a 1 by 1 square. So it is 1 unit squared of area. All right, now I am going to start coloring my square. I'm going to split it right down the middle. And I'm going to color that part of my square. How much of my square is colored? If you said 1/2 unit squared in terms of the area, I'm not going to put the units there, but 1/2, then you would be right. I'm going to come back to my square and say, okay, I can play this game again. I'm going to take half of the area that is not colored in, and I'm going to color it in. That's 1/4 in terms of the area that we are coloring in that particular section. I'm going to take half of the remaining, color it in. That's half of the 1/4 that's up there, which is 1/8. I'm going to take half of that remaining spot. It's a 1/16. And then I'm going to take half of that. And it's a 32nd. I'm going to take half of that, which is a 64th. And I'm going to take half of that. Ooh. And that's a 1/28th. And I'm going to take half of that. And that is a 2/56th. I don't know. You probably get the point at this particular juncture. Now, I still have a little empty spot. Now, that little empty spot's pretty small compared to the entire square at this particular point. And if I keep going with my pattern, there's always going to be an empty spot. But that empty spot's going to get very ridiculously small if I keep going for very long. Actually, this, if we look at the terms, 1/2, and then 1/4, and then 1/8, and then 1/16. That has a T1, or a first term, of 1/2. It also, probably not a great example for this particular reason, but it also has a common ratio of that same value of 1/2. So it has the first term is a half, but it also has a common ratio of a half. And I could pick a different area to begin with, and we can see that doesn't need to be the case for this to work out. Okay. Well, that's interesting. So far, this was like 1, 2, 3, 4, 5, 6, 7, 8. So if I were to just do this 3 times, so this would be the partial sum of the first 3 terms of this particular thing, which is equal to T1, 1 minus r to the n, over 1 minus r, I think. So I'll put this in. So that's actually, if it's S3 specifically, it is 1 minus r cubed. So S3 is equal to 1/2 of 1 minus 1/2 to the 3rd power over 1 minus 1/2. So we get 1 minus 1/8 is 7/8. Half of that is 7/16, all divided by 1/2. So dividing by a fraction is the same thing as multiplying by the reciprocal. So we would end up with 14 over 16, which is the same thing as 7/8. So far, if I've gone 3 terms and I've added that together to get the area of the square here, we would have 7/8 worth of volume, or not volume, sorry, area. So 7/8 of a unit squared. Now, obviously, the whole square, if I were able to fill that all in and not pay attention to my silly rule of doing a half of 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 a half, then I would just get 1 as my answer. We said that earlier, that the area of this particular square is 1. However, let's go to, we said there was 8 terms that we've done so far. So that would be S8 if we did it that way. And again, we would say that that's term 1, which is a half, times 1 minus the common ratio, which is a half to the power of 8, divided by 1 minus 1/2. All right, so in this particular case, we get 1/2, 1 minus, and then 1/2 to the power of 8. 2 to the power of 8 is 256, so this is 1 256. So this is 225 over 256. So this would be 256, the 1, excuse me, is 256 over 256 minus 1 over 256 leaves us with 255 over 256. Oh, it's a mouthful. All right, and then I'm going to divide that by half. So I probably could have done that last time too. So we would get this value that the area so far is 255 over 256. And you can see that this is not like adding 1 to 2 to 4 to 8 to 16 to 32, etc. That just gets really big really fast. This number is not getting really big really fast. This number is getting close to 1, but it's not just blowing up. So if we were just to continue this and put in some very large partial sum, we would still get a number that's just very small in this spot. So it would give us 1/2 times 1 minus something quite small. Actually, let's take a side track for just a moment. We said that S infinity is the same thing as saying the limit as n approaches infinity of the partial sum. For what we're looking at right now, the partial sum is 1/2 times 1 minus 1/2 to the power of n over 1/2. Now, for this particular case, these cancel. That's not always true. But let's take a bit of a look at something I think you'll know the answer to. The limit as n approaches infinity, so we're talking about limits again, of 1 is just 1. What is the limit as n approaches infinity of 1/2 to the nth power? It gets smaller and smaller. Actually, it gets smaller every time you multiply it, but you're multiplying it an infinite number of times. How small does it end up getting? It's going to be 0, or at least approaching 0. So if this approaches 0 for that second part, we would get that the infinite sum gives us 1, which means if you keep drawing little halves of the remaining empty space, half and then half and then half and then half, you are going to end up getting 1 as your area, which makes a lot of sense from a physical point of view. I mean, if you keep going an infinite amount of, and this just gets so small that you can't even describe how small it is, I basically just colored in the whole square. So I would end up getting just 1 as my answer. Now, that means that this is something you can describe with an infinite sum and get a finite answer. This is a convergent series. So when we go back to this and we say, what conditions cause an infinite geometric series to be convergent? Let's look at the piece of this that was really important. When we looked at our S infinity, n approaches infinity. There's only an n in one position in our formula. That one position, let me get a highlighter instead of what I'm using. That one position is right here. And so the only place that matters is this thing right here. What is going to cause that to not blow up? Well, this number has to be a particular type of number, in a special range of values. So again, if you haven't yet thought of this idea, which is what I had asked you to do earlier, maybe take one more pause and think, what values here would make this not blow up? So if I had, for instance, a 10 there, 10 to the power of infinity, uh-oh. 1/2 to the power of infinity, that's okay. What was 0 to the power of infinity? That's okay too. So that thing is our common ratio. And what we've basically said is that 1/2 for a common ratio is going to be convergent. 10 for a common ratio is not. Well, if you look for a commonality that will cause that to happen, you might notice that values that are smaller than 1 will do it. But the fact of whether it's negative or positive doesn't actually matter. So values that are bigger than -1 and smaller than +1 will work. Now you could argue that 1 would also not blow up or shrink the values. Blow up the values, but they also don't shrink the values either. So you end up with something kind of bizarre that happens in most of those cases. So if it was, for instance, if your sequence was 2 as your first term, and then you have a common ratio of 1, then it's 2, 2, 2, 2, 2, 2, 2, 2, 2. Nice sequence. But if you add 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2 an infinite number of times, that's not convergent either. So we actually do require the numbers to get smaller. And in order to do that, we need values between -1 and 1. Cool. Now, I don't know if whoopsie. Actually, I want to insert a little page here. So, I'm going to write down the partial sum, generally, for any geometric series. So we would have T1 times 1 minus r to the n over 1 minus r. All right, so what we're going to do is I am going to say that our r is in between -1 and 1. And so if it's in between -1 and 1, then there's something I can guarantee when I take this limit as n approaches. So s infinity, which I know is now off screen because I didn't set that up very well. All right, so, holy moles. Oh yeah, I want to go over here. It looks like I'm clicking on the right spot, but I'm not. All right, so we're going to move that over. We're going to move this over, and I'm going to try to remember to not have the background move around on you. I'm so sorry. I'm not fully set up to do this here the way that I'm used to. All right, so what we can say then is that this is the limit of that. T1, 1 minus r to the n over 1 minus r. Okay, so the only thing that matters really is n. So the question is, can we make a comment knowing that this is true? Can we make a comment about what r to the n becomes? When you take the limit, r to the power of n always becomes 0. So since under the condition that r has to be between -1 and 1, that always becomes 0, we end up getting T1 times just a 1 over 1 minus r. Some people use an A. I noticed actually some people on the assignment used an A too. That's cool. I've been using T1 lately, but A's are totally fine too for your terms. That is a nice statement. So if you want to know the infinite sum, if you're sure that this series converges, it's a geometric series, and the r is between -1 and 1, then that's what we do. What was that for our square? Well, T1 was a half, and then 1 minus a half. So a half divided by a half is 1, which is the right answer. What if I were to say that I'm going to give you an allowance. This is like this is the opposite of the well, it actually is. It's decay, but it's the opposite of the grains of rice thing that I do for exponential functions in Precalc A. So if you were there for that, you'll kind of recognize it. So the grain of rice thing is you start out, you win a chess game or something like that, and you ask for your payment. 1 grain of rice on the first day of the month, basically, and for the remaining days of the month, it needs to be doubled, and it becomes this very, very large number. Actually, I think on the chessboard it was just pile them up on the squares of the chessboard. So it was 64 instead of just 30 days of a month. But even with 30 days in a month, it becomes very, very large. So what I was getting at is I'm going to give you an allowance. And that allowance is, oops, I want a blank one. That allowance is $20. And next week I'm going to give you half of that. And actually, let's make it worth our time. So I'm going to give you $100 to begin with. So the 20 you might not have been too excited about. 100 is like, okay, that's good. I like $100. And then the next week after that, I'm going to give you a quarter of that. So I'm going to give you 25. And then I'm going to give you a quarter of that, which is 25 over 16. Then I'm going to give you a quarter of that, which is 25 over 64. And then I'm going to give you a quarter of that, which is 25 over 256. And I'm going to give you a quarter of that, which is 25 over 1024. And I'm going to quit. The idea is that we are just basically, I'm going to be paying you less and less and less and less as time goes on. That's fine. But what if I wanted to know how much money I'm going to have in order to pay you for the rest of all time? Now, you might say, well, you probably won't have to worry about that. Life expectancy isn't all time usually. But let's just, we'll say I'm good for it. I will pay you for, we're going to find out how to make people live forever, and apparently I'm still going to owe you this money. So how much do I have to have set away for this? Well, according to what we just said, as long as the R value is between 1 and -1, which it is here. The R value in our case is a quarter, because I'm always taking 1/4 of whatever was there before. I also know that the T1 value is 100, so that means that our S infinity is equal to T1 over 1 minus R, which in this case is 100 over 1 minus 1/4, which means I have a 3/4 in my denominator, which divided by 3/4, same thing as multiplying by 4/3. So we get 400 divided by 3. So the amount of money I will need in the end is 400 divided by 3, which I guess is like $166.66, and then repeating. So we'll say, just for the purposes of money, $166.67, lifetime. Started out real promising with the $100 up front, but it gets real small real fast, and then once you're past the 25, you pretty much are not getting anything worthwhile after that. Oh, my apologies. That's not what I thought it was. That's 133.33. My bad. So even less than what I had said before. $133.33. All right. So that is, again, an infinite geometric series that works out to give you an actual just number value in the end. Even if you made an infinite list of these and you add them up for all the rest of time, you get a number that approaches this 400 divided by 3. Thank you, limits. Hey, limits are useful. So, this is interesting. This says, can every value with a repeating decimal be written as a series? Obviously, if I'm asking this question, the answer is likely to be yes. And so I guess rather than say if it's possible, let's think about how it's possible. So if I have, for instance, 36.2851, and the 851 is repeating for forever, we can come up with a way to write this as a non-series part together with a series part. Now, I don't want anything that doesn't repeat. So I'm just going to say up front that we're going to take the 36.2 and then we're going to add it to a series. And what's that series going to be? The series is going to be 851, and then that's not thousands, that's 10,000s. So that's 851 10,000s. And then I need to add that to another 851, and then that would be um, 851, and then 3 more decimal places, so 10,000, 10 million. And we would keep going and going and going and going. So we can come up with a fraction way actually to write this by using what we just learned about infinite geometric series, because this part over here is a geometric series. It has a T1 value of 851 over 10,000, and it has an R value of 1 over 1,000. So 3 decimal places that we need to shift over for our next one, so that they don't overlap. So we need this to be an 851 afterwards. So how do we do that? Well, we need to move another 3 decimal places. So that's why the 1 over 1,000. If this was only something that repeated after 2 decimal places, then I would use a 1 over 100, so I shifted over twice. All right, so the infinite series part is going to be S infinity is equal to T1 divided by 1 minus R. And so in this case, that is 999 over 1,000 in the denominator, so that's 1,000 over 999. So 1,000 over 999 times that. So 3 decimal places, crosses out 3 there. And so we would get 851 over 9,990. Now that was the repeating part. We also had the 36.2, which is 362 over 10. So 362 over 10 plus 851 over 990. Now let's why not? 362 times 999 plus, so I'm putting it on a common denominator, all over 9990. All right, so I should be able to do this, because that is just 362,000 minus 362. So that would be 361,638. Plus the other thing, which is going to be 2489. This is taking a leap of faith, so I'm hoping that my mental math was not out to lunch right now, and I will check. So this number should be the exact value representation of the repeating decimal that we came up with earlier. So this fraction, you hopefully learned somewhere along the lines in your math classes that all terminating or repeating decimals are rational numbers and can be written in fraction form. This is our fraction form for our repeating decimal that we came up with. So this one is 362,489 divided by 9,990. Oh gosh. 36.2, 851, 851, and then 9 because it rounds to the next digit. I'm pretty sure that's what I had. So my mental math, I got lucky. Yes. So I'm happy with that. And that particular value is the decimal form. So what we were doing earlier was saying, can every value with a repeating decimal be written as a series? Yes, and actually every value with a repeating decimal can be written as a fraction, and if we actually evaluate the series the way it sets up, you get that fraction. So it can be a nice way to kind of do that. However, some of you might know some tricks anyway to being able to write any repeating decimal as a fraction. So it usually involves tricks with nines, so you basically, if you want 0.7 repeating, then it's 7 over 9, but if you want 0.71 repeating, then it's 71 over 99, and then if you want something that's 3, you use 999. And then what we did here was it ended up shifting 1 decimal place, so that's why it was a 999 with an extra 0 on it, so 9,990. All right, so yes, we can write decimals as repeated geometric, or just repeated addition in a geometric series. All right. Is the following series convergent? If so, what value does it converge? Okay, so all this stuff is kind of, it will take maybe a little bit to sink in, but using it in a case like this is nice and easy. So, is the following series convergent? If so, what value does it converge? All right, so first of all, T1 is 1. Negative 1/3 is our step. So multiply by negative 1/3, you get a third. Multiply by negative 1/3, you get a 9. That's good. So we get a common ratio of negative 1/3. This is definitely between negative 1 and 1. So this is a convergent series. Convergent series, we can use this. Don't use this if it's not convergent. This will give you a number, but that number is wrong. So maybe I'll show you an example of that in just a moment. So this is T1 over 1 minus r, which in our case, T1 is 1 over 1 minus r. R is negative 1/3, so it's minus negative 1/3, which is plus a third. That's 4/3 in the denominator, same thing as 3/4, so there you go. This gives us a sum of 3/4. So it becomes, it's 1, and then it's 2/3, and then, oh gosh, 2/3 is the same thing as 6/9, so 7/9. And then you would subtract from that 1/27, and et cetera, and it bounces up and down kind of around this value of 3/4 and gets closer and closer and closer to it. So easy peasy. Very nice calculation in order to do the S infinity in a case like this. Once you have the comfort with identifying when it's okay to use, and let me show you, like I said, when it's not okay to use, and of course it does not work. So if I said 2, 4, 6, 8, oh nope, that's arithmetic. Now let's try that again. 2, 4, 8, 16, 32. So that has a T1 of 2, and it has a common ratio. I should think of my examples a little more carefully. The last time I had that, it was 1/2 and 1/2. Let's do one that's 3, 6, 12, 24, 48. So this one has a T1 of 3, but it has a common ratio of 2. So at least the number's different. All right, so add those numbers together, infinite amount of time, go. What's the answer going to be? Infinity. Okay, so you're correct in saying that the answer here is going to be infinity, or does not exist, if you wish, no real number. Okay, let's just double check that. Bet you didn't know the answer to this is negative 3. So if you add those numbers together for an infinite amount of time, you actually get an answer of no, you don't. All right. So don't use that if it doesn't fit the conditions. If you're not between a negative 1 and a positive 1, then you might regret it. Now, that's not to say I don't know. That this is beyond me. I know that if you add together, for instance, the harmonic series, I think it is. Maybe it's not, but it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. You supposedly get negative 1/12. I don't know anything that my brain doesn't work like that. You can, some of the parts of people showing that mathematically make my skin curl a little bit, but that's it's all right. Okay. So is the following series convergent? If so, what value does it converge? Okay, now this is tricky because you see the decimal. Oh, you see the decimal and you're like, oh yes, decimals, this is good. Psych, it's arithmetic. So there's no common ratio. So if you multiply 1 by a number, you would get 9/10 if you multiply by 9/10. But if you multiply by 9/10 again, you get 81/100. It's not 8/10. It's really close, but it's not correct. So this is not a geometric series. This is arithmetic. You're subtracting or adding -1/10 to it both times. It does not have a converging. It's not a converging series. It doesn't have a finite answer. All right, so that is good for now. Just play around with it a little bit. Take a look at some of the work in 1.5 in the textbook that's there, and yeah, I will. Let me know if you have any questions. I'll put some practice up for you, and I'll give you one last assignment probably on Thursday morning. Take care.